add more flavor to the overall story of this Riverwood calamity. There's something in the water. We need to learn more about water in order to understand what could potentially be contaminating the water. That's next chapter. Next chapter we will look at the possible contaminants of water. But we need to all be on the same page looking at the basics of water. First of all, last time we were talking about boiling point. There's oftentimes a lot of confusion over the differences between boiling and evaporation. So, does anyone know the difference between boiling and evaporation? Nobody? Yes?
Boiling is when it's still a liquid but it's getting heated, and then evaporation is when it actually gets heated enough where it turns into a gas.
You know, there's a lot of truth in what you said, but there's also some missing pieces. First of all, how do they all relate? They both involve liquid turning into a gas. I like that. You said that. They both involve liquid turning into a gas. But evaporation, my friends, can happen at any time. If given the choice between having to put a hand in an evaporating container of water or a boiling container of water, choose evaporation. Because evaporation can happen at any temperature. You can have a wet garment that you want to dry, hang it out to dry on a very, very cold day where the temperature is 0 degrees Celsius, and it will dry eventually. It might take a while, but it will dry. Eventually, all that water on the shirt will evaporate. Okay? It would probably be a better idea to put it in the dryer, increase the temperature, because by increasing the temperature, you increase the evaporation rate. Now, boiling doesn't take place at any temperature. Boiling takes place at one specific temperature, and that is the boiling point of water, 100 degrees Celsius. Next, evaporation only takes place at the surface, because if water is just being heated by the natural environment, it is being heated from the surface down. But if water is being heated in an unnatural environment, like in a stove or in an oven, or maybe even we're talking about a collection of water under some kind of geothermal lava hot area, then it's going to be heated from the bottom up. And that was something else that Jeffrey was alluding to. Evaporation can only happen at the surface because that's where it's receiving heat. Boiling is going to happen throughout the liquid because it's receiving heat at the bottom. So boiling is from the bottom up. Evaporation is from the top down. Now, we talked about steam. Can we see steam? No. Actually, what we call steam, we can see. Yes, we can see steam. But steam is not the same thing as water vapor. Steam is what is water vapor that have combined together with other water vapor molecules to form tiny little droplets. Clouds can be thought of as steam. So steam is evidence that water vapor is there. Steam is the condensed water droplets. When water vapor encounters colder temperatures, they condense into what we call steam or fog or whatever. So you cannot see water vapor. You can only see the evidence that water vapor is there. Watch this video. So after 70 minutes, the pot is completely empty. Where's the water? Gone. And after 70 minutes, was it completely evaporated?
No.
When you're relying on heat from the environment, it happens very slowly. So what is it about boiling point of water that is important to life? I'll give you a clue. Unusually high or unusually low?
High.
Unusually high. It is unusually high. Water's closest cousin is a molecule by the name of H2S. H2O is our friend water. H2S is its closest cousin. How have you encountered H2S? Well, now, if you've ever cut the cheese and you're sitting there going, oh, please, let there be no smell. Please let there be no smell. And there is no smell, then what you mostly released was methane. Methane is odorless, colorless. Can't tell it's there. But if you cut the cheese, then you're going, oh, no. Oh, I hope I'm the only one that can smell this. And then people around you are going, oh, man, who did that? First of all, never admit it. Just go, oh, that's disgusting. Who did that? Just play along with it. If you cut the cheese and you can smell it, then you are smelling our water, our best friend water's closest cousin, H2S. H2S is actually a normal molecule. Okay? It also has another cousin, H2SE, that acts just like it does. And they have really, really low boiling points, like in the negative degrees. So what does that mean to us? That means that we're way above its boiling point. So for us, it's going to exist as a gas, which is a really cool thing. Because if it was like water, it would exist as a liquid. And every time you would cut the cheese and you've had some beans, you've had some potato salad, then all of a sudden you'd be going, oh, I forgot my Depends. Oh, man. And you're leaving a trail behind of H2S liquid. So, if we have to depend on water, if water is mostly what we're made up of, aren't we glad that water has such a high boiling point compared to its closest cousins? Because if it was like its closest cousins, would water even exist in the liquid form here? It'd be like a gas. So now you know more about cutting the cheese than you ever wanted to know.
Really starting to freak me out.
What is another important physical property of water critical to plants? Water's sticky. It has a high surface tension, which once again, if it wasn't so sticky, life could not exist. We depend on its stickiness because that's how water draws up, or that's how plants draw up water from the roots. If water wasn't sticky, then water would not go up the xylem in a plant. Plants could not exist. No plants, no humans. Sorry. Dead. Water is sticky. Does H2S, can H2S stick like that? No. Water is weird. It's unusual. It is remarkable. It is bizarre. And yet for us, it's perfectly natural because we're mostly made up of water. So water's made up of what? Atoms of hydrogen and oxygen. What are hydrogen and oxygen? What are these things?
Elements.
They are elements. Which of course begs the question, what are elements? Whenever you see a number, gang, that's time to get back into your notes. We go on little segues of stuff that I think is important for life. Now you know about cutting the cheese. But then we have to go back to what the state considers important. What are elements? Elements are pure substances that are made up of only one type of atom. Pure substances made up of only one type of atom. There are approximately 118. they're always fighting back and forth over the last couple. Some scientists will say now 117, some will say 118. Some will be very, very resistant to change and say, no, there's only 116. But there's just a little bit over 100. Okay? You can find all these where? On your best friend. It's the periodic table of elements. Here are a few. If you don't like these, you've got 118 to choose from. Take out your best friend and choose your favorite 5. Or 6. These are the building blocks of all of what we call matter. All matter is made up of these building blocks. Well, macro matter, compounds, mixtures. We can think of things there are actually things smaller than an atom that is also made up of matter. Where can you easily find all the elements? The periodic table of the elements. So, if elements are only made up of one type of atom, what are compounds? Made up of 2 or more, but here's a very important thing to remember. It's not a random making upper. It is always a constant, simple whole number ratio. There's order to all of this. It's not just some sodiums and some chlorines all stuck together. It's always 1 sodium, 1 chlorine. Always found in the same whole number ratio. What are some examples of compounds? Water, H2O, CO2, O2, NaCl, sodium chloride, NaCl is table salt. The salt that they add to the roads right before a snowfall is de-icing salt, that's CaCl2. Sugar is C12H22O11. If it's not C12H22O11, then it's not sugar. That's glucose. Very good. Limestone, one of the parts of concrete, is CaCO3. Where else will you find concrete? In your antacid tablets. Your antacid tablets are basically flavored concrete. Well, you don't want it to have its original flavor, do you? Tiny amounts of concrete. Rust is iron 3 hydroxide. Where's the iron 3? What is this hydroxide? You'll find out soon enough. All right, so these are atoms. These are molecules. Hydrogen comes as a couplet. Oxygen, for every 1 oxygen, you have 2 hydrogens. That makes it water. Nitrogen, for every 1 nitrogen, you have 3 hydrogens. That makes it ammonia, which is that stinky gas in Windex. About how many elements are found in nature?
50.
About 90. 90. Well, what about the others? You said 118. Yeah, those are man-made. That's right. About how many compounds are there? Bazillions. Bazillions. So what holds these compounds together? Bonds. Chemical bonds. Bonds. Chemical bonds. What do we call it? What do we call the smallest subunit of a compound? The smallest particle of a compound. Atoms are made up of these things. We call them molecules. Molecules. You were. So water is a compound. But the water that we drink is not a compound. We've been talking about how I like Dasani, I like Aquafina, I like Oak Ridge drinking water. Okay, by the fact that we have different opinions about water tells you that there must be other things in water that give it taste. And we have really differing opinions on the different mixtures of water. Mixtures. A mixture is two or more substances that are together but are not chemically combined. If your parents are married, then they are a mixture. Now, they formed you, they formed a compound, but they are a mixture. Your dad is still your dad, your mom is still your mom. My wife wishes that it wasn't that way because she's been trying to change me for 25 years and she's succeeded on some things, most things she hasn't, because I am still me. I have not become something new. We're married, we are a mixture. We each bring in to our marriage our own distinctive personalities. Now, let me give you some advice. This is much more important than chemistry. If you're going into a marriage thinking, I will change Ben Walls after we get married, all these things that irritate me, I will change. It's not going to work. It's just going to, he's just going to irritate you worse. Okay? So don't go into a marriage thinking, hey, I can live with what really irritates me about Gracie. Those glasses. I wish she didn't have those glasses. Ah, better. What are the two kinds of mixtures? Heterogeneous and homogeneous. This kind of goes along with what we were talking about. There are two kinds of marriages, right? Homosexual marriages, heterosexual marriages. The prefix homo and hetero is the key here. If it's a homosexual marriage, what does that mean? Same gender, right? If it's a heterosexual, hetero means not opposite, means different. Different. So a heterogeneous mixture is going to be one that appears to be made up of different things. All mixtures are made up of different things, but some of them appear, some of them it's obvious, some it's not. Air does not appear to be made up of different things, and yet it is. Muddy water is made up of different things. Yes, Ben?
That's the definition for heterogeneous.
Yes, a mixture that is not completely uniform. A mixture that is not completely uniform. A mixture that does not look like it's made up of. It has to be made up of more than one thing. Period. I can see it. Some examples. Put salt and pepper together. Can you see the salt? Can you see the pepper? Muddy water. Shake it up. It looks like it's one thing, but after a while it settles out. You can see the mud. You can see the water. Oil and water. How about oil and vinegar dressing? Folks, if it says shake before using, guess what? It's not just a mixture, it's a heterogeneous mixture. If you can see the different parts to it, it's heterogeneous. Look at your tabletops. That is a faux marble finish. It's not marble. It's a fake. It's F-A-U-X. That's French for fake. A fake marble. It's trying to make you think that it's marble. It's not marble. The really cool thing about marble, it's a metamorphic rock. It comes in swirls or dots, depending on the type of marble. It's beautiful. Can you see the different parts to it? Yeah. All those are little mineral pockets. If you can see the different parts, it is heterogeneous. If you can't see the different parts, if it appears to be a compound, because you can't tell it apart, then it's homogeneous. So you're writing things down. Let me tell you a story. An interesting story. Okay? It starts with being in the cafeteria this afternoon. Notice, look around, see people taking their milk carton and shaking it. And after this story, you will laugh at them. Okay? Why do they shake their milk? Because they saw their parents shake their milk. Why do their parents shake their milk? Because they saw their parents shake their milk. Why do their parents shake their milk? Because they saw their parents, your great-grandparents, shake their milk. Why did their great-grandparents shake their milk? Asher? Because it was a heterogeneous mixture. See, folks, milk from a cow is a heterogeneous mixture. It will form different layers. That's how we get, have you heard skimming the fat, or skimming the top, or skimming the bottom? You can actually skim the top of the milk in order to make butter. You can make you can make cheese from different parts of the milk. Okay? They had to shake the milk, or else the first few drinks would be really watery, and the last few drinks would be almost like sour cream. You'd have to use a spoon. You had to shake the milk. Back in the 1940s and 50s, they came up with the homogenization process. That homogenization, I have a hard time saying that word. Milk is usually made up of big giant molecules. Homogenization breaks them down into little particles that can stay suspended in the water. So it doesn't settle down to the bottom. So you don't have to, your parents didn't have to shake it, probably their parents didn't have to shake it, and you don't have to shake your milk. Don't shake it. Laugh at the people who shake it. Now, chocolate milk is probably a heterogeneous mixture. I would probably shake chocolate milk because I think those big chunks of chocolate tend to settle down on the bottom, and if you don't, then it's not uniform. So chocolate milk, shake. Regular milk, don't shake. There's no reason to shake it. That's right. Laugh at people who do. What is another name for a homogeneous mixture? A solution. A solution. Two parts to a solution. They are solute, which is the stuff that gets dissolved, and solvent, which is the stuff that does the dissolving. Solute is what gets dissolved. Solvent is that which does the dissolving. Air, what is the solute? Air, what is the solute? And what is the solvent? Let's think about it. Air, what are the two main things in air?
Nitrogen.
And?
Oxygen.
Good. Nitrogen and oxygen. Which one do you have the most of? Nitrogen. So whoever you have the most of, that's your solvent. Whoever you have the least of, that's your solute. So air, the solvent is nitrogen. The solute is oxygen. Water mixtures can be classified into three possibilities. They are suspensions. They are colloids and solutions. Let's take down suspension first. Suspension, very large, easily seen particles will disperse if the food or the medicine says shake before using. It is a suspension. It is a suspension. Yes. I think we're on the second page, number 22. A lot of liquid medicines are suspensions. It says shake before. How about Pepto-Bismol? You know what I'm talking about? You got to shake it or else it's really kind of nasty. Actually, it's kind of nasty without shaking it, with shaking it, but it's you got to shake. Cough medicine. If it says if you got to shake it, it's a suspension. Chocolate, milk is a suspension. A colloid is what we make milk into. when we take big giant molecules and make them small enough so that they stay connected to water throughout and form a web throughout, that's a colloid. Milk is a colloid. Milk is a colloid. A solution is made up of teeny tiny little particles. Salt particles, sugar particles, carbon dioxide particles. Teeny tiny little particles that are dissolved in water are solutions. Salt water. Those salt particles are so teeny and so tiny, it looks like it's just water. It's not. It's a mixture, but it looks like it's just water. Drinking water has all sorts of stuff dissolved in it. The solvent is what? In drinking water, the solvent is, what do you have the majority of? Water. Good. What are some of the solutes in drinking water?
Dirt.
Dirt? I hope not. How about drinking? What? In drink, like Dasani, they do add a type of salt, like sodium nitrate. Okay. What else? Well, we've talked about this. Yeah. Come on. You can smell this one if they add too much of it. They're not going to add sulfur, but you can smell sulfur in water. That would be a solute. How about chlorine? Chlorine in water. How about fluoride? Fluoride ions. That's for your teeth. Yeah. Whole milk is going to have all these big giant molecules in it. Here's another picture of whole milk with the big giant molecules. Non-fat milk, they've broken down some of the molecules. Whole milk is 4%. That means 4% milk fat, 100% water. Okay? What is it? What's the next one down? I don't drink milk anymore. I'm lactose intolerant. 2% is 2% milk fat, 98% water, and the rest of the stuff. And then skim, I think, is 0.5%. 0.5%. How can you tell a colloid from a solution? The Tyndall effect. Tyndall effect. If you can see the laser going through, you have a colloid. If you don't see the laser going through, because it goes in and comes out the other side, but you don't see it go through, it is a solution. If the mixture is so thick that the laser gets completely blocked, then that is a suspension. Suspension. What's that? Solution, you wouldn't be able to see it going through. Colloid. Colloid. Okay, how about this one right here? Colloid. This one? Solution, but you don't see it going through. This one? If you can see it going through, which I can, right there, it's a colloid. All right, I would write this down. This is important. Somewhere on the side of your paper, make 3 beakers. No, I'd keep it near your notes. I'd keep it on your notes. All right. Beaker A is going to contain teeny tiny little particles. Beaker B is going to contain larger particles. Beaker C is going to contain giant molecules that a lot of them have settled out and some of them are still up in the water. Now we're going to shine a laser through them. First one, the laser goes in, comes out the other side.
Oh. This one goes straight through.
The second one, you can see it go straight through and out the other side. And in the third one, the laser goes in, but it doesn't come out. So what kind of mixture is made up of teeny tiny little particles that never settle out and are so teeny and so tiny that they cannot reflect light at us? What do we call a mixture that's made up of medium-sized particles that are large enough to reflect light back at us, allowing us to see the laser? And what do we call a mixture made up of big, giant molecules that are so big that they will completely absorb the light? Believe it or not, we went through, if you're a checklist person, we went through 1B, 5 through 9 today. So you can have the pleasure of checking all those off. I want you to do for homework, and it should not take you long, though you may need the internet. I want you to do for homework 4 through 11. In other words, complete worksheet 1.2 for tomorrow. It'll be graded tomorrow. 4 through 11. 4 through 11.